Number 39. Which of the following procedures will produce a buffered solution? So let's start with actually number 3. Notice I didn't write any sort of reaction out for number 3. And the reason is because in 3 there's not really a reaction. You have sodium acetate and you have acetic acid. And those two definitely will make a buffer. You have a weak acid and a conjugate base. So certainly number 3 is one of those situations. Now you might look up here and you might say with these other two situations, well, no, they aren't, because like for instance sodium hydroxide and acetic acid, that's a base but that's not its conjugate acid, and vice versa. But what we're getting to up here is that sometimes we make buffered solutions during reactions, during titrations, or just mixing of acids and bases. So for these two, we're actually going to have to draw out reactions. So 3 is definitely an answer choice, but let's look at number 1. So number 1, we have sodium hydroxide reacting with HCl. Now the amounts may matter, but they don't in this particular case, because you notice where you make NaCl and H2O. We do have an acid, and we have its conjugate base. Cl minus is its conjugate base. But this is definitely not going to be a buffer, and the reason is because HCl is a strong acid, and so it needs to be a weak acid in its conjugate base to be a buffer. So 1 is out. Let's look at 2. So in 2, we have sodium hydroxide with acetic acid. It's going to make sodium acetate and water. Now we definitely have a chance for a buffer here because we have a weak acid, acetic acid, and its conjugate base, which is acetate ion. Whether or not we have a buffer, though, depends on if we have both of these left over in the reaction. So let's see, we're talking about equal volumes. In this one we had 0.5 molar, and this one we had 1 molar. So you can see that the sodium hydroxide is going to completely be consumed, but there is going to be some of this left because the sodium hydroxide is the limiting reagent. And of course, as the reaction goes on, we're going to make some of this as well. So we are going to have the acetic acid and its acetate anion. So 2 is a good answer. We decided 3 also was, so it looks to me like the answer is going to be D. Let's look at number 40. The following titration curve shows the titration of a weak base with a strong acid. And it seems right. The pH is really high, so it definitely is starting with a weak base, and it decreases as you add the acid. Now they want to know which of the following most accurately approximates the pKb of the weak base. Well, we don't usually see bases, starting with bases and adding acids. We're more familiar with this style, where you have an acid initially and you're adding a base to it. So let's look at that for a minute. And you remember that the Henderson-Hasselbalch equation can help us find pKa's. Not pKb's, but we'll get to that in a minute. So in the Henderson-Hasselbalch equation, you remember that there's this magical point about halfway to the equivalence point, right about there, where the concentration of the acid and its conjugate base are the same. And the reason we can see in the reaction up here is, let's say we have 1 mole of the weak acid. By the time we've added half a mole of OH, which is halfway to the equivalence point. Remember, adding 1 mole would be to the equivalence point. But when we added a half a mole, well, this is completely consumed, but we have some acid left, and we will create half a mole of this weak acid. So at this point, about halfway to the equivalence point, is where the concentration of the acid and its conjugate base are the same. And so this goes away in the Henderson-Hasselbalch equation, and the pH will equal the pKa. So all we'd have to do is come over here, and if the pH was 3, then the pKa would be 3. So simple enough. Now we can apply the same idea to this graph up here, is if the equivalence point is right about there, after having added this much acid, and the equivalence point looks to me like it's about at a pH of 6.5 or 7. Well, halfway to adding as much acid is about there, and so the pH looks like it's between 9 and 10. Now you might think that the answer is going to be A then, but that wouldn't be true, and the reason is because that is the pKa is 9.8, not the pKb. So we need to subtract it from 14, and so the answer looks to me like it's going to be D.